Hello everyone, in this lesson we will learn about the graphs and properties of logarithmic functions together. Mathematics learning emphasizes continuity and continuity. Let's first review the content we learned earlier. Do you still remember the concept of logarithmic functions? The general function y is equal to the logarithm of log with a as the base x. A is greater than 0 and a is not equal to 1, which is called a logarithmic function, where x is an open interval from 0 to positive infinity in the domain of the independent variable. Do you still remember the origin of logarithmic functions? According to the relationship between exponent and logarithm, the exponent function y is equal to the power x of a. A is greater than 0 and a is not equal to 1, obtaining x as the logarithm of base y with a, and then obtaining the logarithmic function y as the logarithm of base x with a dot dot. It can be seen that exponential functions and logarithmic functions are closely related. Do you still remember the methods and processes for studying the graphs and properties of exponential functions? First, draw a function graph based on the analytical expression, and then use the graph to summarize its properties. In this lesson, we will still use this method to learn the graphs and properties of logarithmic functions. So we need to draw some specific logarithmic function graphs. Which one should I draw first? Some people say to draw a simple and special one first, because the ratio of logarithmic rows has two ranges, greater than 1 and between 0 and 1. First, choose y as the logarithm of x with a base of 2. We still use the point drawing method. What is the logarithm of 0.5 equal to two bases? -1. What about the logarithm of 1? It's 0. By multiplying 2 times by 4, according to the properties of logarithmic operations, we can obtain 2. Using 2 as the base and 8 as the logarithm, some people say it is 3. So please use a pencil and ruler on your notebook. Draw a sketch. This results in the graph where the logarithmic function y is equal to the logarithm of x with a base of 2. Please pay attention to the image features. Image to the left. Approaching the outer axis infinitely and extending infinitely to the right, we drew a graph of y as a logarithmic function with a base of 2 and x. We also need to draw another function graph within the range where the base is greater than 0 and less than 1. We draw a logarithmic function graph where y is equal to x with half as the base. Can I draw a line? Of course. Is there any other way? We can use the same method as the previous index. We found that it is related to logarithmic images with 2 as the base x. It can be obtained from the bottom changing formula. The logarithm of base s is equal to half, and the logarithm of base s is divided by the logarithm of base 2. According to the properties of logarithmic operations, we can obtain a negative logarithm with a base of 2x. Some classmates have discovered it. This function graph is symmetric about the x-axis with the function graph we just drew, so we can use geometric symmetry to draw it. We rely on symmetry. On the graph of the logarithmic function y, which is equal to half of the logarithmic function x, take any midpoint m as the symmetry point. Based on symmetry, we can create several more symmetry points and then connect them for multiplication and division. Everyone, take a look. The image is symmetrical about the x-axis. So far, we have drawn two special logarithmic function graphs within two different ranges. Obtain two special logarithmic functions for bases greater than 0 but less than 1 and bases greater than 1. Can these two function graphs help us observe and summarize their properties? In order to facilitate our full observation of the properties of the function, we should draw more graphs of single-digit functions. When the base is greater than 1, please pay attention to the graph changes of the logarithmic function. When the ratio is greater than 0 and less than 1, please everyone, pay attention to its image changes. We have selected a few special ones. Images can summarize its properties. Please complete this form. Everyone, please take a look. There are two different situations where the base is greater than 1 and the base is larger than 0 and smaller than 1. We first summarize the domain of definition. The domain of a logarithmic function is an open interval from 0 to positive infinity. We can also see its domain of definition from the image. Now let's take a look at the range of values. Based on the relationship between the rows mentioned earlier, we can also observe that the range of values is are below. I will summarize two other properties. Is the image over a fixed point? The images all pass through fixed point 1 and 0. When x equals 1, y equals 0. Some students said that they learned about the concept and properties of logarithms earlier, and they also know that with as the base, the logarithm of 1 is always equal to 0. Of course, it is also possible. An important point is monotonicity. When the ratio is greater than 1, monotonicity is an increasing function. When the top is greater than or less than 1, monotonicity is a decreasing function. As can be seen from the image, the left image shows an upward trend from left to right. The graph on the right shows a decreasing trend from left to right. When increasing the function, for any x1 greater than x2 and greater than 0, it is assumed that the logarithm of the base x1 is greater than the logarithm of the base x2 with as the base when decreasing the function. Yes, any x1 greater than x2 greater than 0 exists. The logarithm of x1 based on a is smaller than the logarithm of x2 based on a, and vice versa. So for this property, we can summarize it intuitively from the image or analyze it mathematically. So what problems can this knowledge help us solve? Everyone has also noticed. The key points of this property are exactly the same as those of exponential functions learned earlier. This indicates that there is indeed a connection between exponential and logarithmic functions, and we can further consider it. According to the relationship between exponent and logarithm, from the exponential function y equal to the power x of a, we obtain x equal to the logarithm of log with as the base y, and then obtain the logarithmic function, where log has as the base and x as the logarithm. I can see it now. Their domain and value range are exactly interchangeable. At this point, it is said that they are inverse functions of each other. Please note that the reverse here does not simply mean the exchange of domain and value range, but rather the correspondence between independent variables and function values. That is to say, the reciprocity of operations. Please refer to example 1. Compare the sizes of two values in the following questions. The first one is a log with a base of 2 and a multiple of 3.4. The second one is the logarithm of log with a base of 8.5. Think about it. Where have you seen this type of problem before? Although these two values are fixed, they are acceptable. As a function of motion change, when the independent variable x takes two special values, the corresponding function values are very good. Because function y is equal to a base of 2, multiples of s are increasing functions in the interval from 0 to positive infinity. So 3.4 and 8.5 can be seen as different values between them. 3.4 is less than 8.5, so the logarithm of 3.4 with 2 as the base is smaller than that of 8.5 with 2 as the base. Let's look at the second question. A log with a base of 0.3 is good for 1.8 logarithms, and a log with a base of 0.3 is good for 2.7 logarithms. We can see it as two different function values where function y is equal to the logarithm of x with a base of 0.3. Because the function y is equal to the logarithm of x with a base of 0.3, it is a decreasing function in the interval from 0 to positive infinity. 1.8 is less than 2.7. The logarithm of 1.8 with a base of 0.3 in log is greater than the logarithm of 2.7 with a base of 0.3 in log. Let's take a look at the third question again. This base number a, it just means it is greater than 0 and not equal to 1. What should we do if the scope is not determined? How many categories are needed for classification research? By the way, there are two categories. Why are there cases where the base is greater than 1 and where the base is greater than 0 or less than 1? Yes, the monotonicity is different. Everyone must understand that the monotonicity of both exponential and logarithmic functions varies depending on the range of ratios. When a is greater than 1, the function y is equal to, with a as the base, and the x multiplier is an increasing function in the interval from 0 to positive infinity. So the logarithm with a as the base 5.1 is smaller than the logarithm with a as the base 5.9. Another scenario is when a is greater than 0 and less than 1. The function y is equal to a as the base, and the logarithm of x is a decreasing function on the interval from 0 to positive infinity, so the magnitude relationship is exactly the opposite. Let's continue with example 2. Compare the sizes of two positive numbers m and n that meet the following conditions. Everyone should carefully examine the topic. Observe the structural characteristics of the given equation. Everyone noticed that the first one is in logarithmic form. The base numbers are all determined to be 3, and the true numbers are m and n. How to compare the size relationship between m and n when logarithms only have a size relationship? Through monotonicity. Why use monotonicity? Because in monotonicity, there is a mutual transformation between the unequal relationship between independent variables and function values. Because the function y has a base of 3, the logarithm of x is an increasing function from 0 to positive infinity. So the logarithm of m with a base of 3 is smaller than the logarithm of n with a base of 3. So the independent variable m is less than n. The second question is based on the mutual transformation of the relationship between the independent variable and the function value in the monotonicity of the function. Everyone should pay attention to the differences between example 2 of this question and example 1 of the previous question. Although both involve monotonicity, they come from different perspectives, studying from different directions. Let's take example 3. The standard pH value for drinking water is between 6.5 and 7.5. The so-called pH value refers to the concentration of hydrogen ions in a solution. The acidity or alkalinity of a solution is measured by its pH value, and the symbol for pH calculation represents the concentration of hydrogen ions in the solution in moles per liter. Let's take a look at the first question. Based on the properties of logarithmic functions and the above formula for calculating pH value, explain the relationship between the acidity and alkalinity of a solution and the concentration of hydrogen ions in the solution. What is a change relationship? That is to say, the increase or decrease in hydrogen ion concentration results in changes in pH and acidity. Let's mathematize this symbol a bit. Everyone sees it. Then y is equal to the logarithm of x with a base of 10. Its opposite number. So because y is equal to a base of 10, multiples of x are increasing functions from 0 to positive infinity. So y is negative with a base of 10, and multiples of x from 0 to positive infinity are subtraction functions. So the pH value varies. The increase of hydrogen ion concentration in the solution leads to a decrease. That is, the higher the concentration of hydrogen ions in the solution, the stronger the acidity of the solution. Let's take a look at the second question. The concentration of hydrogen ions in pure water is known to be 10⁻⁷ moles per liter. Please calculate the pH value of purified water. Everyone can directly enter the formula for calculation, equal to 7, so the pH value of pure water is 7. The third question. It is known that the pH range of a certain type of drinking water is 6.8, which is less than the pH value of 7.8. Please determine the concentration range of hydrogen ions in this type of drinking water, different from the second question, the opposite question. Because the pH value is greater than 6.8 and less than 7.8, we substitute it. Got it. Please take a look. The logarithmic value of hydrogen ion concentration based on 10 ranges from -7.8 to -6.8. So how to solve it? How do I use this king? Using the concept of logarithms. Convert -7.8 and -6.8 into pairs with a base of 10. What is the power of 10? So based on monotonicity, we can conclude that the concentration of hydrogen chloride is between 10⁻⁷.8 and 10⁻⁶.8. The unit is moles per liter. In this class, we can reflect and summarize from two aspects. Firstly, there is the method of thinking. We obtain images from analytical expressions, which means reading data from the image by counting to form. Then, from the image to the property, that is, from form to number, to view form through numbers. The second is that the idea of classification integration compares the impact of two different scopes on monotonicity. The second aspect is the practice of knowledge. We should thank the great mathematician Euler for helping us understand the relationship between exponents and logarithms. Exponential functions and logarithmic functions are not only related in terms of concepts, graphs, and properties, but also in terms of the types of problems they solve. Therefore, we need to learn and apply the two as a whole.